continue on the chemical properties of alkenes. We are going to look at formal properties, and then we shall know that we have finished them. The first one we shall look at for today is additional hydrogen bromide in presence of peroxide. Now, previously we looked at additional hydrogen halides across a double bond, but we said that reaction follows what we call the Markovnikov's rule. But now, if it is in presence of a peroxide, we can have a peroxide illustrated as ROOR, whereby this R can be an alkyl group. Do you see that? So if there is a peroxide, then it means that the reaction mechanism will follow what we call the anti-Markovnikov's rule. And in the anti-Markovnikov's rule, the bromide will attach itself to carbon with more hydrogen atoms, and then the hydrogen will attach itself to the carbon with the less hydrogen atoms across a double bond. And we have said that this kind of change that is the opposite of Markovnikov's rule is what we call anti-Markovnikov's rule. And I'm going to use an example to illustrate this anti-Markovnikov's rule. So a clear example, I'm going to use propene, CH3, CH double bond, CH3. This is CH2. That is CH2. I'm reacting it with HBr in presence of a peroxide. That R can be CH3. So it can be CH3 or CH3. However, I'm just generalizing it. Do you see that? Now, if there was no peroxide, remember, the double bond would have attacked hydrogen, and then the hydrogen would have attached itself to carbon with more hydrogen atoms across the double bond. Then the Br would have come here, so we would have formed 2-bromopropane. But now, since we have the presence of the peroxide, the vice versa will be true. It's the bromide that will be attached to the carbon with more hydrogen atoms. Then the hydrogen will come here, leading to the formation of CH3, CH2, then CH2Br, CH2Br. Do you see that? The reason why we are saying so is because there is a peroxide. So the peroxide changes the mechanism. Let's look at the mechanism. Now, this mechanism will follow what we call free radical mechanism. What is the free radical mechanism? Free radical mechanism is the mechanism that is sparked off by radicals. So this peroxide, because of this instability, is going to split into radicals. Do you see that? This bond, oxygen bond, will be split evenly. It will be split evenly. Each will take one single bond, one single electron. This will lead to the formation of 2 ROs. Now, the moment these 2 ROs are formed, remember radicals are very reactive species. They are going to attack the HBr. So we are going to have RO, one of the ROs is going to attack our HBr. Do you see that? So this hydrogen bromide bond will break off in an attempt to react with the RO radical. This will lead to the formation of an alcohol, ROH. Do you see that? And then plus this bromide. Now the bromide, since it has taken only one electron, it will be a what? A radical. It will be a radical. Now it is this bromide radical now that is going to spark off a reaction with an alkene. So in that case, we have CH3, CH double bond, CH2. Now this is going to react with the bromide radical. Do you see how the reaction mechanism is different? So this double bond here is going to make sure that one of the bonds breaks into radicals. So this upper bond can break. So one of the electrons will come and lead to a reaction with the bromide. This bromide, when it comes in, it will be attached to carbon with more hydrogen atoms. Of course, this other electron on this bond will remain on this what? On this carbon. This will lead to the formation of CH3. CH. Now this C has a radical. Do you see that? Then CH2Br. CH2Br. Why? Because this Br has been attached to carbon with more hydrogen atoms. Now, this compound here is going to be forced to react with an alcohol formed here. Do you see that? And therefore we are going to have CH3, C radical H, then CH2Br. This one is going to be forced to react with ROH. So I'm going to write it in the form of H, then ROR. HOR and ROH, they are the same. Do you see that? So there's going to be a split of bonds. This one is going to come and then it's going to react with that carbon, which has a radical, and then we shall form again a radical of RO, which will combine with the excess one here to form our peroxide again. Do you see that? So this will lead to the formation of CH3. Then this carbon has gained an extra electron, an extra hydrogen, forming the CH2, then CH2Br, CH2Br. Of course, plus our byproduct, which is R4. That's our byproduct, which is R4. So basically, this is the end of the reaction because this byproduct R4 is going to react with an excess of this, leading to a formation of our peroxide again. You see that? So we may not so much care about it. What we are so much interested in is the formation of that compound, which actually is 1-bromopropane as required. Our next example, our next reaction that we are dealing with is the reaction with potassium permanganate. Now it is known that the double bond is able to undergo oxidation. Yes. So what we know about potassium permanganate or potassium manganate 7 is the fact that it is a strong oxidizing agent. And because there is unsaturation on the double bond, the carbon-to-carbon double bond can be oxidized by the potassium permanganate in presence of an alkaline solution or in presence of the OH. In presence of the OH. This leads to formation of what we call a diol. This is an alcohol which has two functional groups of the OH group. And the OH group functional groups are attached to the carbon with the double bond. And we are going to look at an example of a reaction which would take that format. For example, if you have, I'm going to write a general one. If I have RCH double bond CHR, maybe this can be R prime, maybe it's different from that. They might be the same. It really does not matter. So I'm using this in presence of, I'm going to oxidize using the manganate 7, potassium manganate 7. In presence of alkaline medium, that is OH minus. Now, this will lead to the formation of, I will have an OH here and an OH here. That's what we call a diol. So it is going to be RCH, OH, then CH, OH again, then R prime. That's what I'm saying. It's an oxidation reaction leading to the formation of a diol with an OH group being attached to the carbon atoms of the double bond. This reaction is used to test for the presence of a double bond. But it's important to note that is in alkaline medium. In fact, I need to note it somewhere. Maybe I can put it here. This is an oxidation reaction leading to the formation of diol. Yes. Maybe I can attach it here. A reaction with alkaline. I can react it here. I can put it there. Reaction with alkaline potassium permanganate. Because if the potassium permanganate is in the acidic medium, the reaction will not take place. So we must make sure it is in the alkaline medium. That's the OH. What is an alkaline? An alkaline is simply a soluble hydroxide, potassium hydroxide, sodium hydroxide, ammonium hydroxide, and sometimes additional hydroxide, leading to the formation of diol. That means that the purple solution of potassium permanganate will turn colors. It means if you are in a practical exam, let's say, and then the instruction is add potassium permanganate to a compound, it means that it is more likely that if alkaline potassium permanganate turns colors, then the compound was an alkene. Is that okay? And that one you will see it's so common in your practical exam. So a simple example I can use, I can call this CH3. This is CH. Then that is double bond CH. Then this one I can call it CH2 CH3. In presence of the manganese. And also the alkaline medium. And also the alkaline medium, you may cheat, you may not cheat, it really does not matter here. The OH, one of the OH will come here, the other will come here. That will be CH3, CH, OH, then again CH, OH, then CH2, CH3. CH2, CH3. Someone can ask for the name of this compound. How do you name this compound? The first thing to note is the number of carbon atoms in the longest chain, which is 1, 2, 3, 4, 5. 5 carbon atoms. So it is a derivative of pentane. Pent for 5, right? But there are two. There are two what? There are two OH groups. So it is a diol. But the first one is on position number 2. The second one is in position number 3. So it becomes pentane. Pentane. 2, 3. 2. Pentane 2, 3. Diol. Pentane 2, 3. Diol. So that compound we call it pentane 2, 3 diol. To mean that there are 2 OH groups, and the first one is on position number 2, the second one is on position number 3. Yes, so let's look at the second class property. In this case, we are calling it ozonolysis. Ozonolysis is the reaction between alkenes and ozone. Ozone is simply O3. That is a trioxide, or oxygen that is triatomic. Do you see that? But it's supposed to be in presence of tetrachloromethane. This leads to the formation of an ozonide. Do you see that? The ozonide, I'm going to show you its formula, its structure formula, so that you can appreciate it. Now, this ozonide, under hydrolysis in presence of zinc, this will lead to formation of carbonyl atoms. Let's look at the mechanism of such a reaction. An example I'm going to bring, maybe I can generalize. I have RCH, double bond, CH, R prime. That is an alkene. Just generalize any alkene. Now I'm going to react with ozone. Ozone is O3. But we have said in presence of carbon tetrachloride, or you can call it tetrachloromethane. You can call it tetrachloromethane. We are going to form an ozone. Now, the structure of ozone is like this. Then we are having another one here. Of course, there is a CH here, then CH here, then R prime. Now we are going to break the carbon to carbon bond, but we are going to form a bond here that is going to join carbon and carbon via oxygen, and we are going to form another bond here connecting carbon to oxygen, and another bond here connecting carbon to oxygen, and then we shall connect them. So we form almost a pentagon ring around the double bond. Do you see that? This is what we are calling an ozonide. Now we are saying if in presence of water or during hydrolysis, this ozonide is going to break down leading to the formation of carbonyl compounds. Remember what we said about carbonyl compounds? We said carbonyl compounds are characterized by a carbon double bond oxygen. This is their functional group, a carbonyl. However, if on both sides we have alkyl groups on both sides, this one is called a ketone. If on one side we have an alkyl group, on the other side we just have hydrogen, this one is called an aldehyde. So carbonyl atoms, carbonyl compounds are classified into aldehydes and ketones. This one is being aldehydes, and then R prime, C double bond O, then R. These ones are called ketones, whereas these ones are called aldehydes. So it is important to note the difference in the carbonyl groups. What matters is the fact that for both cases there is a carbon oxygen double bond. Do you see that? Now, if you come here, we have RCH, then CHR prime, then we have O here, and here, like this. If it undergoes hydrolysis in presence of zinc in presence of water, we are going to split the compound into two. We split it. We form an aldehyde this side and also an aldehyde this side. Why? Because you see for both cases, this carbon is bonded to only one alkyl group, even this one is bonded to one alkyl group. So it is a typical aldehyde that is going to be formed. Because for an aldehyde, the carbon with the functional group is only attached to one alkyl group. So it means we are going to form, if I form an aldehyde on this side, it's going to be RC double bond O, then H. Then plus this side is going to be R prime C H, then double bond oxygen. Do you see that? So we have formed a couple of aldehydes. So when someone can ask, when do we form ketones? I can give an example. Remember we have said these R's can be alkyl groups CH3, CH2CH3. You see that? So when I want to form a ketone, I have to make sure that one of these carbon atoms has a branch. So for example, I'm going to have CH3 as my R prime. Then C, where I have hydrogen, I'm going to put CH3 like that. Do you see that? Then the double bond, CH, then maybe CH3. CH, maybe CH3. In that case, I am going to, in most cases, we prefer to combine the steps so that you can avoid the ozonate, because the ozonate looks ugly sometimes. So you are allowed to say in a first reaction, I am using ozone in presence of carbonyl tetrachloride. Do you see that? Then I will also allowed to say in my second reaction, I'm hydrolyzing in presence of zinc. So it means I have avoided the ozonite, leading to the formation of, I'm just going to split this compound. Do you see that? Across the double bond. Then on each of the carbon atoms, I attach carbon oxygen double bond. So in this case, if I attach here oxygen, carbon double bond, it shall be CH3, C, then double bond O, then CH3. Do you see that? What about here? What about here? Here I'm going to attach the double bond on this carbon, leading to the formation of CH3. Then C, double bond O. Then what? H. Do you see that? So this one here has become an aldehyde. Whereas this one has become a what? A ketone. Has become a ketone. Why? Because the double bond to form here, there is already a methyl group. And therefore, this is a typical ketone. Whereas this one is a typical aldehyde. So, ozonolysis helps us to form, aldehydes. The other thing that ozonolysis helps us, members, is to reduce the carbon chain. You see that? For example, when you look at this compound, it has how many carbon atoms? 1, 2, 3, 4, 5. But we have split it into simpler compounds. This one has 3 carbon atoms, this one has 2 carbon atoms. That means when you are in synthesis reactions, for example, if you are in synthesis reactions and you are required to form a smaller compound being given a bigger compound. So in your steps, you have to consider ozonolysis because it can help you to do what? To reduce the number of carbon atoms in the chain. Of course, if you are interested in the ketone, the aldehyde will be a byproduct. Remember, we have said in organic chemistry, sometimes the byproduct is neglected. But that is only in case when the byproducts are not so many. Like, for example, if you remember the chlorination of alkenes, in presence of EV, we said you form very many compounds. So it is a mixture of compounds which cannot be chemically or physically separated. So in that case, you avoid. But in such cases where you have only one byproduct, it is easily separated using chemical means because there are very many compounds that can separate a ketone from an aldehyde, and we shall study next time. I can give another example here. For example, if I have CH3, CH2, then C, I can create CH3 there, right? Then double bond, CH, CH2, double bond CH2. It's like that. I want this compound to undergo ozonolysis. So in my first step, I'm using ozone in presence of carbon tetrachloride. In my second step, I'm using zinc in presence of water. Since there are different steps, you have to indicate step number 1, step number 2. So what will happen here is that the compound will split across the double bond. You see that? The compound will split across the double bond, and each carbon sharing the double bond will develop a carbon-oxygen double bond. Do you see that? So it means here I will create a carbon-oxygen double bond, even here I will create a carbon-oxygen double bond. What will I form? This will form CH3, then CH2. Do you see that? Then C, this carbon here, which share the double bond, is going to create a double bond between carbon and the oxygen. Then this CH3 is still there. Do you see that? Then plus. Now this carbon here will also develop a carbon to oxygen double bond. So it is carbon, oxygen double bond, then hydrogen. There are 2 hydrogen atoms. In fact, somebody might ask, sir, what would be the name of these carbonyl compounds? For example, if I begin with this one is a ketone, right? Being a ketone, it has 3 carbonyl atoms, so it is a derivative of propane. So it becomes propanone. This is an aldehyde with 2 carbonyl atoms. So it is a derivative of ethane. So we call it ethanol. So what we shall say, if it is an aldehyde, you add the suffix AL. In fact, it might even be NaL, because even N will always come. But what we are interested in is AL. If it is a ketone, you add the suffix ONE to the name of the what? Of the alkane. If this was propane, it becomes propanol. If this was ethane, it becomes ethanol. Now look at this. 1, 2, 3, 4. 4 carbon atoms. Do you see that? So it is going to be a derivative of butane. Butanol. But now, butanol. We may not be interested in the position of the double bond because it will always be on carbon number 2. Even if we put it here, it will still be on carbon number 2. When you look at this, only 1 carbon atom is a derivative of methane. But now we add suffix AL, it becomes methanol. Remember what I'm saying, that these reactions here help us in reducing the number of carbon atoms in a chain or in a skeleton. Now, looking at our last chemical property of alkane, let's say the undergo polymerization, especially ethene undergoes polymerization to form a common compound which is used in our daily lives called polythene. You see that polythene can be used for making wrapping papers, cups, plastics, many other things. There are many other alkenes that undergo polymerization, but I want to just pick only ethene. You are saying in the presence of oxygen or peroxide at a pressure of 1,500 atmospheres at a temperature of 200 degrees. So we have a reaction equation to illustrate what we're talking about. So we have ethene. So there are N molecules of ethene. They undergo polymerization. So in that case, this double bond will be used to react with more other monomer molecules of ethene. For example, you have CH2. So this is the bond. The double bond has been used to create another bond between CH2 and another CH2. And the double bond here will be used to create another bond between CH2 and CH2. And this double bond will be used to create another like that, leading to formation of a big compound, which we are calling polyethylene. Do you see that? So it means the number of carbon atoms will depend on how many ethene molecules. How many ethene molecules have taken part in this kind of polymerization. So the number is 8. So I'm just going to generalize and say, maybe just consider this because it is being repeated 8 times. You see that? So I'll form my compound CH2, CH2. Do you see that? I said this is repeated 8 times. This is repeated 8 times. Do you see that? So this is the structure formula of polyethylene. This is the polyethylene we are dealing with. Polyethylene. This is the polymer, and then this is the monomer ethene. Do you see that? I hope you have studied these definitions of polymerization in O level, but still we shall study them in applied chemistry. So what we are just simply saying is these monomer molecules, they bond together. N of them, N can be 1,000, N can be 100, so it depends on the concentration of ethene molecules, right? So that's why the A is not specific. We just write N to mean that a polyethylene can have as many ethene monomers as N, but of course it is defined, it cannot go beyond a certain number. So that is